Hello again. This is part 2 of the October 7th, 2021 Introduction to Finance class. So let's jump into the material. And we were just talking about present and future value. Now we're going to move on to similar things, although we're taking it to the next level now. We're going to talk about annuity payments. Now, an annuity basically is a stream of payments. It could be a regular payment of a bill. It could be an interest payment. It's basically anything that is a steady stream of something, some type of a numerical value. And in bonds, certainly interest payments are part of an annuity. In an insurance product, when we talk about personal insurance or personal finance, we'll talk about annuities. But the concept of an annuity is, for our purposes at this moment, it's a steady stream of revenue or expenses. It's a regular steady stream. And for our purposes right now, it'll be the same amount each time. Obviously, there are some payments or expenses that vary over time, and so that makes the calculations a bit more complicated. Nevertheless, they will stay with the basic ones for right now. There are a number of different factors to consider with an annuity, and you'll need to know which one is going to be applicable for the problem that you're trying to solve. An ordinary annuity basically exists when equal payments occur at the end of each time period. So for example, if you buy a bond that pays interest once per year, you buy the bond now, and a year from now, you will get the first interest payment, and so on and so forth for every year that you will have that bond, and every year that that bond will be in existence. So that would be a payment at the end of the period. On the other hand, let's say that you were going to get the payments right now, up front, starting right now. So in the event of, say, a charge that would begin, let's say rent, your rental payment is going to be due not a month from now or not a year from now, it's going to be due today. So an annuity due is when the calculation involves a payment that you get at the beginning of each time period. Okay, so that's it. Ordinary annuity, payment at the end of each period. Annuity due is a payment at the beginning of each period. So let's look at some examples here. The basic equation, and again, we're going to be using tables for something like this, but think in terms of the payment, and it's going to be multiplied by 1 plus whatever the interest rate is. And that'll be multiplied by the number of time periods that you have minus 1. And then divide that number by whatever the compound interest rate is. So it gets a little bit hairy, if you will, at the outset, but we're going to break that down for you and make it easier to understand. So let's use tables for that particular period. So here's an example. You plan to invest $1,000 each year beginning next year for 3 years at an 8% compound interest rate. What will be the future value of the investment? Well, we know that the payment's going to be $1,000. We know that the interest rate is going to be 8%, and we know that it's going to be for a 3-year period. So if you plugged in all the numbers, which you see down here, this is what you would get. You would wind up with $3,246 as the amount of the future value of that annuity. So you put away $1,000 each year, and at 8%, you do it at the beginning of next year, which is really the next year payment at the end of this period, the end of this year. You do that for 3 years. You will come up with 3246. Now, what's an easier way to do that? Well, if we go to the charts in the back, you'll find out, first of all, remember you're talking $1,000. We're talking 3 years. So on the far left column, the 3-year entry right here at an interest rate of 8%. So you find where the two numbers meet, and in this case, it meets at 3.246. So the future value of an ordinary annuity, you take that factor, multiply it by 1,000, and you get 3,246, which just happens to be the number that we had using the formula. If you're using a calculator, on the other hand, again, it's not too difficult. Again, you just got to make sure you're entering the right information in the right location. So if you're going to invest $1,000 a year, you'll plug in 1,000. Again, change it to a negative. And then you're going to enter that as in the payment function, the PMT key. Remember, right now we're just using the top row of keys. There are 3 years involved, so N equals 3. So you plug 3 in and then hit the N key. The I/R, the interest rate key, is 8%, so hit 8 and then hit that key. We already talked about the present value of $1,000. That's that payment. And then you hit the future value of, and you hit the future value key of to get 3246.40. Now, we're not using, if you notice, we're using the payment key and not the present value key. The present value key would only apply if it was one payment, but this is a series of payment. It's an annuity. So that's why we use the PMT key instead of the PV key. Okay, so that's for finding the future value of an annuity. Those are the keys or the chart that we'll use. Now, suppose we want to use the present value of an annuity. Again, this calculation is a little bit more complicated. You take the payment that you're going to be making. You're going to multiply it by 1 minus 1 divided by 1 plus the interest rate, and multiply that by n number of years. Divide all that by the interest rate. So the PVA, the present value of an ordinary annuity, is what we're trying to solve for. The periodic equal payments, PMT, compound interest rate is the lowercase r, and a lowercase n is for number of periods. Excuse me, let's look at an example now. So to get the present value of an annuity. So you're going to receive $1,000 each year beginning next year. And you're going to do that for 3 years at an 8% compound interest rate. What will be the present value of the equation? So you can plug in the numbers if you wish, the $1,000 for this formula. You'll plug in the 3 years and the 8%. You'll come up with an annuity worth today of $2,577. So that means then that if you you invest $2,577 at 8% a year, where the payment, that 8% is compounded every year, you're going to wind up with $1,000 for that 3 years. So put 2577 in at 8%, you'll get the next 3 years $1,000 each of those years. How can we calculate that? Using a chart. Using the present value of an annuity chart at the back of your book, that's table number 4. We are given 8% as the interest rate. We're also given 3 years. So look where those two numbers meet and they meet with a factor of 2.577. Multiply 2.577 by $1,000, and you wind up with 2,577. Okay, so it's just a question of knowing the right chart to use. Next, if we were going to use a calculator, in this example, it's slightly different. We will, N is the number 3, that's 3 years. I/R is an 8% interest rate. The payment amount is $1,000. Okay, we're going to receive the $1,000 payment. And the present value is what we're going to solve for. We're going to hit the present value key, and we are going to get a negative 2577.10, which essentially means that's the amount of investment that you need to make. Remember, an investment is typically represented by a negative number. So just to say that again, 3 years, you hit the N key, 3, enter N. The I/YR is 8 for 8%. The payment key is 1,000. So you'll enter 1,000 and hit the PMT key. And finally then hit the PV key. Then you'll get a minus 2577.10. I mean, in reality, your present value is 2,577.10. Okay, just for the calculator's purposes, you'll just use a negative number. Now, of course, because we're dealing in present value, we're not looking for the future value. The future value key is typically going to involve a lump sum. So it's not going to be applicable in the case. So we're only going to use those 4 keys for this example. Moving right along. Now, if you're trying to find interest rates or time periods for annuities, remember, just like what we talked about before, there were 4 possible variables. Here we have 5 possible variables. The future value, the present value, the interest rate, the number of periods, and this time we have to add in the payment amount. Okay, when you're talking previously, we were talking about a lump sum of one number. Here we're talking about a payment, an annuity, if you will, of a series of payments. So it also helps you, if you do know several of these numbers, you should be able to solve for the missing value with the calculator keys that you have. Okay, so let's use an example. Suppose that you have a future value of an annuity of 5751. So a stream of payments is worth in the future $5,751. The annual amount that you're going to pay in is $1,000. The time period is 5 years. So what is the interest rate for this problem? So said another way, we know that we're going to pay in $1,000 a year for 5 years. We know that the value at the end is going to be worth $5,751. What interest rate do we need to earn in order to get to 5751? Using the financial calculator, we know the future value is 5751. The payment is going to be a negative $1,000, because remember, it's an investment. It's money going out to make the investment. So we will hit a negative number. We'll hit 5 for the N key. And then since we're trying to find the interest rate, we'll hit the I/YR key. And we'll find that that answer is 7%. Okay, which again does agree with what we have here. So using the future value of a dollar ordinary annuity table number 3 in the back of your book, we know that we're talking about a period of 5 years. We are looking for an interest rate. We know that 5751 is the future value. We know that the annual payment is $1,000. So if we divide the annual payment into $5,751, that will give us the factor that we need to look up. The factor in this case is 5.751. It just so happens that 5.751 at 5 years comes out to a 7% interest rate. And that's what you see over here on the second column from the right. Okay, so that's finding the interest rate. All right, now, suppose we're looking for the number of years. Well, it's basically the same number. You use the same chart. It's just that now we're using a different part of the chart to get the answer. So we know the future value is 5751. We know the annual payment is $1,000. In this case, we know the interest rate is 7%. Okay, again, we know that the factor we're going to need is going to involve dividing 1,000 into 5751. That will give us a factor, again, of 5.751. And it just so happens that when you get the 7% interest rate, go down the column, you'll see that 5.751, that's the factor, that is for year number 5. So again, it will take 5 years for a payment to be made at 7%, $1,000 a year to get to $5,751. Okay, now just talk a little bit about loan payments right now. Loans, and we'll talk more about these, especially when we talk about personal finance. An amortized loan is a loan that is equal payments for a specified period of time. And typically it's going to involve interest and principal payments. The fact that it's amortized means that the principal along with the interest is being paid over a period of time. The process is solving for a periodic payment amount. The amortization schedule, this is a schedule of the breakdown of each payment between interest and principal, as well as whatever the remaining balance is. When we study mortgage interest payouts and mortgage interest payments, we will look at an amortization chart so that you can see numerically how the interest and principal change hands as the payment is being made. And remember that in the examples we're giving right now, we're using the same amount of payment each time, not a variable payment. Okay, so moving on here, compounding or discounting more than once per year. So this involves taking the basic equation where you have the future value, where you take the present value, multiply it by 1 plus the interest rate that is divided by the number of compounding periods. So let's look at an example. Compounding periods, and then also take that to the number of years times the number of compoundings. So let's look at an example to help you understand it. What's the future value of a 2-year $1,000 payment of 8% with an 8% loan, semi-annual compounding? Okay, so $1,000 is what your payments there's a semi-annual compounding. So you would just plug in the numbers there that you see here. You will wind up with the result of $1,169.90. So this is a 2-year $1,000 loan at 8% with semi-annual compounding. $1,169.90 is going to be the value of that. Now we're starting to get a bit more complicated. How can we simplify the process? Well, To do that, if we're using the tables, let's, for example, look at the future value of an annuity. I'm sorry, the future value of the present value. To get that number, and above here, you see that we do have the basic formula. Now, here's the way to you'll use the chart to do this. When you are having compounded periods, the compounding is entered differently than it would be if it was simple. So, for example, semi-annual compounding means 2 payments per year. Interest is calculated on an annual basis. So if you have an 8% annual interest rate, but you are compounded semi-annual, semi-annual is 2 payments. So what that means is the 8% is the equivalent of 4% every 6 months. So let me say that again. A semi-annual payment, which is twice per year, if the annual interest rate is 8%, what you really are doing, if it's a semi-annual compounding, you're taking a payment of 4% twice a year to come up with that 8%. So, and also because it is 4%, you're getting half of the payment each 6 months. You're doing twice as many payments. All right, it's a 2-year period, but the payments are semi-annual. So there really are not 2 payments, but it's 2 times 2, or 4 total payments. So what did we just do? The number of periods has, in this case, doubled from 2 to 4 because it's semi-annual compounding. The interest rate, because payments are made twice a year, the interest rate is divided in half. So if we go to the table in the back of your book, instead of looking for the 8% table, we look for the 4% table. And instead of looking for the 2-year number, we look at the 4-year number. So they meet at 1.170. And remember, we're talking $1,000 loan. 1,000 times 1.170 rounded for you comes out to $1,170, or as in the example here, $1,169.90. So that's compounding. Compounding, if it's semi-annual compounding, divide the interest rate in half, but double the number of periods. Okay, the same thing would work with a calculator. So instead of using 2 periods, N is 4. The I/R, instead of it being an interest rate of 8%, you enter 4. And the present value will still be entered at $1,000. That's not going to change. So you enter a negative number of $1,000. Hit the future value key, and you will get the 1169.86. So again, there's some rounding in there, but that is within pennies. That is your answer. So that's it using, it's the same concept, and that's how you would use it with a calculator. Okay, a couple other items here before we finish up, and that is this. So there are 2 important means of representing interest rates. There's an annual percentage rate, and there's also another interest rate, which is the effective annual rate. The annual interest rate is taken by multiplying the interest rate charged per period by the number of periods in a year. So the annual percentage rate, let's use an example. Let's say you're charged 1% a year. So you're not charged 1%. Okay, remember all of your numbers are typically put into an annualized number. So 1% a month is the equivalent of an annual percentage rate of 1% times 12 for 12 months, or 12%. So your annual percentage rate, your APR in that example, is 12%. On the other hand, the effective annual interest rate is the true interest rate when compounding occurs more frequently than annually. There's your formula right there. So the effective annual rate equals 1 plus whatever the interest rate is multiplied by the number of compounding periods minus 1. So what, for example, is the effective annual rate on a credit card with a rate of 18% annual percentage rate and monthly payments required? Okay, well, if you are charged 18% and it's over a 12-month period, that's 1.5% per month that you are paying. And that really compounds out, because remember, that's 12 compounding periods that occur. Everything is put into an annualized number. So with 12 compounding periods, you've got to take that into account. So with an interest rate, which may be 18%, okay, so divide that by 12, it gives you 1.5% per month. Break that out then over an entire year, and then minus the number 1, and that gives you 0.1956 or 19.56%. Okay, moving on now. Annuity due. So remember what we were saying before. An ordinary annuity is where the payment is made at the end of the period. An annuity due is when the payments are due at the current period. Well, the formula now you can see is starting to get kind of complicated, but don't fear, okay? The key here is that there is an additional calculation of 1 plus the interest rate, and you multiply that by whatever your future value, whatever the future value due is. Let me give you an example. This is not as complicated as it may seem. Okay, here's a whole calculation up on the top here. You have $1,000 each year beginning now. You get the payment now, not a year from now, but now. For 3 years, the interest rate is compounded annually at 8% interest. What will be the future value of this investment? So the shortcut to do this, instead of using the whole formula, now you'll notice that your answer here is $3,506. But the quicker way to do that is go to the future value of $1 ordinary annuity. Now remember, the ordinary annuity is the payment at the end of the period. The way to get around that, however, is to take that result and multiply it by 1 plus the interest rate. So we go to the future value of an ordinary annuity. We see that at 8% for 3 years, that future value is 3.246. But again, that payment is at the end of the period. That's an ordinary annuity. We want to make this an annuity due. So we're dealing with $1,000 investment. You multiply $1,000 by the 3.246. It gives you, as you see on the bottom of your slide there, it gives you $3,242. But to get it as an annuity due, so that the payments are at the beginning of the period, you multiply it by 1 plus the interest rate. The interest rate is 8%. So 1 plus 0.08, which is 1.08, multiply that by $3,246. It will give you $3,505.68, which is rounded to $3,506. This gives you the annuity due amount. So now you have gone from the ordinary annuity amount where your payments are going to be made at the end of the period, 3 periods in this particular case. Instead, if you want to make the payments come at the beginning of the period, then you're going to get a slightly higher number because the money is coming to you quicker. You're getting it now instead of at the beginning of the period. You're getting it at the beginning of the period, not the end of the period. So you're going to multiply the future value ordinary annuity amount by 1 plus the interest rate, and that's going to give you the annuity due amount, which in this case is 3,506. Okay, hopefully this makes all sense to you. You'll be able to replay this. Also check your textbook and also any of the materials that I gave you that can be found in Canvas. And then I will provide you with a 5 or 6 question quiz for this. Okay, very good. And thank you very much again. I appreciate your efforts in this and bearing with me. And we'll see you then a week from today. Take care.